Welcome back to the plenary session on first day. It is my pleasure to kind of welcome Professor J. Srinivasan from Center for Atmospheric and Oceanic Sciences, IISc. He will talk about tropical climate variability.
Okay. Yeah, thanks. So good afternoon. We had a long day. We had lectures on radiation, convection, and dynamics, and so on. So I don't think we want to have a very heavy lecture. It'll be very simple. It will follow up on what Professor Bellon talked about an hour back. It's following that. She talked about axisymmetric conditions. I'll talk about much more confined conditions. Okay. So I just want you to remember that Earth is a very complex system. There's all kinds of scales, temporal and spatial. And in this program that has been arranged for you, all these scales will be covered in the next 1 week or more, okay? And my focus will be not on these scales, which many other talks will be on these scales. Mine will be more on much larger scale, where you don't have to worry about transients and other things. We want a simple understanding of the monsoon. That is the purpose, okay? And I want you to understand the difference between mid-latitude and tropics. When I got into this field from engineering, I always got puzzled by why are mid-latitude different, okay? You see the big difference here. This is something all of you heard about, ITCZ in the Pacific, and this is vertical lines which move this way, okay? So there's a fundamental difference between tropics and mid-latitudes, and that you must understand, okay? Now one more example, a nice horizontal line, inclined line slightly, because of the change in rotation as you go along from here to here, okay? So these go regularly, okay? So the forecasting in mid-latitudes is much simpler than in our area. I thought our people were dumb. They were not dumb. It's a tougher problem, what we have. And that's the difference. This is the focus of this course. Well, in mid-latitudes, it is driven by the jet stream, okay? And one more example covering India. India in winter gets what you call a hint of mid-latitudes. This line you see here in November, many years ago, is because of cold air coming from mid-latitudes, meeting the moist air coming in the tropics, and you get a line, okay? This you don't get during monsoon. You get only in winter, okay? You can keep watching. The windy sort is very good. You can keep watching. It'll keep moving all the way back. And this is, of course, our ITCZ in October, when it has come back right now it's somewhere here. And this is the best example of ITCZ over the ocean, very long one. And so this is easy to understand because very uniform boundary condition. Over India, it's a bit difficult because there are influence of mountains and land and so on. And I'll skip that. Okay, so this all of you already have heard about it. So this is the most important system in the tropics, which is the one which leads to the Hadley cell, which was discussed by Professor Bellon. Okay. Now the most interesting part about this is what happens in the Pacific and what happens in the Indian region. In the Pacific, what you saw remains pretty much the same place throughout the year, okay, from Jan to December. But over India, you can see a sharp transition, okay? And so that's what we understand how this system exists and how it moves, and different from those other systems which move left to right, west to east. This is an animation of rainfall over Europe. You can see it is moving steadily to the right, okay? And it can be predicted very accurately. Those of you who have seen this can see that forecasts are very accurate, okay? We cannot do that accurate forecast in India. And in mid-latitude, you have fronts. You have a cold air and warm air, and in that front, you get those rain. We don't get it in India. In India, we don't get front except in winter. So in this, of course, the warm air rises above the cold air, and there's condensation. but the role played by water vapor and latent heating is much weaker here than in India. Okay. Now, this is a point I want to remember. If you plot the latitudinal variation of temperature, okay, zonal mean conveniently, you will see this is a region which we normally talk about. This is the tropics and this is mid latitude. The biggest difference is there's a sharp gradient in the mid latitudes. There is almost no gradient here, okay? And this is the basis of one of the models in the tropics called WTG, weak thermal gradient model, okay? I think maybe covered in one of these lectures. I won't cover that, okay? Now, this is the animation of how rainfall and clouds move in the tropics. And what I want to remember is, it moves like this. It doesn't move like this, okay? It starts from Indonesia in winter, goes across, and it comes over East Asia and then India, okay? So this was not understood by people before the satellite era, okay? And I'll tell you what misunderstanding is caused, okay? Now, this is the other system which will be talked about by one of these speakers, is MJO along the equator, which is a unique region of the Earth because the vertical component of rotation is 0, okay? So you will see all along the equator, the system move, and there will be a model by, I think Gilles, you'll talk about it, right? One of these, going to talk about that. Now, the other important difference you must understand between tropical and latitude is the rainfall. In our region, we are used to seasonal variation of rainfall. So in London, you will hardly see any rain difference, okay? That's a fundamental difference in the climate, in the ecology, in the culture, okay? Our culture is being tuned to live in this climate where rain occurs only 4 months a year, 8 months is dry, okay? Here, rain comes throughout the year. There are no problem with water. Remember that. Okay, so there are so many scales here, indicate a monsoon, all the way from diurnal to millennial scale, and spatial also, all the way from a bacteria which can cause droplet to condense on a nuclei, all the way to what we are going to talk about, okay? Now, the earliest theory, of course, all of you have read in your school textbook, is a Lancy contrast theory of monsoon, which is completely wrong, okay? But it is still taught. I don't know why. It still has not been removed out of the textbooks. You must know why it is wrong, okay? So this is traditional view that it is a Lancy breeze. And it's easy to understand. Land heats up, air rises and goes back. But this is not monsoon because it's a very shallow convection. This will not give you deep convection, very shallow convection, and lasts a few hours, okay? And I can tell you, I was in IIT Madras for 5 years as a student. We had no fan. We are not allowed to have fan, okay? At those days, they said students should have a tough life, not an easy life. And we survived because IIT Madras right on the coast, and you get this sea breeze coming in the afternoon, okay? So that's very local phenomenon. It is not a global phenomenon, okay? So why it is wrong? It's wrong because Lancy quartile surface temperature is small once the monsoon onset occurs. The minute it occurs, all of you who lived in India know the day after the monsoon, temperature drops for 5 to 10 degrees, okay? So the Lancy contrast does not exist during the monsoon. It exists only in the onset phase, otherwise it doesn't exist, okay? Second is that Lancy contrast temperature in Africa is very large, but rainfall is low there. Look at Sahara. It's very hot. Arabian Sea is reasonably cold during the monsoon. It should set up a huge convection, right? Does it? And then, in good monsoon years, when the rainfall is good, this contrast is small, okay? And actually, no one has discovered any relation between delta T and rainfall. Not a single formula exists, okay? And just to show you, this is the surface temperature from reanalysis. You can see that except for Sahara, which has a large Lancy contrast, over India there's hardly any contrast. And it was shown clearly by Kotwale and Rupagwa a long time back, more than 20 years ago, that in deficient monsoon years, delta T is high. In good monsoon years, delta T is other way, negative, okay? So the key point is that Land-sea contrast is a consequence of monsoon, not the cause of the monsoon, okay? So I want you to get into it because you've been taught wrongly in your school years, it won't go away, you have to get rid of it, okay? Yeah, and one more point you're right, this is in May, where monsoon not come, you have the shallow convection, which is the land-sea breeze. Only in July that the convection, this vertical velocity, convection goes up to middle of the atmosphere. So this is the big difference between pre-monsoon land-sea breeze and the monsoon convection. And the key point is this. And the other thing people should have asked when they have satellite data, if land-sea contrast is so important, how come the highest rainfall occurs in Bay of Bengal and West Pacific, not India? Okay? That should have bothered people. Why is the highest rainfall occurring in Bay of Bengal and West Pacific, not over India? Okay, now this has been nicely mentioned by Clift and Plum in this book, but somehow nobody reads it, okay? The point is that there's a land-sea contrast. The contrast is in heat capacity, not in temperature. Ocean has a large heat capacity. It stores the sun's light from January to May in the mixed layer, and that's what's available rest of the year, okay? So that is the thing we should focus on, not the temperature, okay? Now, the other important mistake was made because of land-sea contrast theory, is to think Tibet is very important. Because Tibet is a large landmass, okay? Elevated, 5 kilometers. So Flown proposed more than 70 years ago that the elevated heating of Tibet caused the monsoon. And it became so popular that the geologists used that to predict when Himalayas rose. They looked at the proxy data of rainfall and they said, when the rainfall increased, Himalaya must have risen. Okay, that was a theory written up 30 years ago. Later on, they found the proxy data was wrong. Then they admitted that Tibet is not playing a role. Okay? As a matter of fact, one of my students did this work, he's going to talk here later. He removed Tibet, nothing happened to the monsoon. It got delayed slightly, of course, but monsoon is still there. Okay? Monsoon is very big, Tibet doesn't control it. Okay, to show that clearly, Booz, who's going to talk next week, he showed that the highest temperature at the 250 hectopascal, around 10 kilometers, is not over Tibet, over India. Because that warm layer is determined by latent heating, not by surface heating. Okay? That's a very nice result that was published by Booz. Okay, then there's another nice paper. It shows that we find that strong Indian monsoon is preceded by a colder temperature over Tibet. Okay? So all that should completely shut down this land-sea contrast theory. Okay, now I will not talk about this, but this will be discussed in this program for the next few weeks. There are two kinds of modes we'll talk about. One is related to the moisture feedback, it's called the moisture mode, and the other is related to latent heating feedback and dynamics, okay? So you'll see here, I think there's a whole talk on moisture modes in this course. But what I'm going to talk about is not, all these are relevant on a time scale of a few days to a few weeks to maybe a season. But I'm going to talk about seasonal mean and longer scale, so I won't talk about this, but this is very important, okay? So now I'm going to focus on important thing which was missed by people for a long time, that is the fundamental role played by water vapor in tropical climate. And the reason why it was not well understood is because water vapor plays 3 different roles, independent roles, okay? One is because it's a greenhouse gas. It's more powerful than carbon dioxide. People don't realize that. It has a huge impact on the radiation budget of the troposphere. Next, it is lighter than air, so it gives you buoyancy. Third, when it condenses, it releases latent heat, okay, which drives global circulation. And also it affects cloud. When it condenses, it changes the cloud and radiation. And when it comes to ice, affects albedo. So all these 5 different roles are there, and it's not easy to disentangle. Actually, I'm not seen any paper. I would like to see a paper in which you take a GCM, you remove the radiation effect of water vapor, run the model. Okay, see what happens. Make water vapor equal to 29, run the model again. And the third is make latent heat equal to 0. You'll get 3 different climates unrelated to what we see today. Only then we'll understand the role of each of these. Of course, they interact, unfortunately. So it's not going to be easy to understand, but it's worthwhile running 3 simulations, one without greenhouse effect, one without latent heating, one without buoyancy. You'll get 3 different results, and I think it'll give you insight. And I think that is the role of GCM. GCM's role is to help us understand the complex system by deliberately shutting down some part of the system. Okay, so this is again a summary of what I'm only going to focus on the greenhouse effect, condensation, and buoyancy. Okay, to point out how important water vapor is, if you look at the onset of the Indian monsoon, which is normally very sharp, not always, and I chose the year 87, this is the kinetic energy. You can see how sharp it rises. It goes up 10 times in the onset date, okay? And notice that before that, water vapor has to reach a critical value. If the column water vapor does not cross 40 kg per meter squared, you cannot have an onset, okay? But we don't have a simple theory why. Okay? I was for a long time hoping they can come up with and all of you know about Rayleigh number, which is used in engineering to talk about free convection. I was thinking of a moist Rayleigh number, which has to cross a critical value for the onset, but so far I've not found one. Not easy, okay? Because the flow is turbulent. Normally we deal in laminar flow, that's very easy. Turbulent flow is more complicated. So I've not found a simple, but I'm sure there is a way to come up with a non-dimensional parameter, which when it crosses a critical value, onset occurs. But again, there's a whole session on that here. So we'll see what they say. Okay. Now, to show how interesting water vapor is, I'm going to quote a paper of Gilles, who is a very original thinker in this area. He showed this data from West Pacific, how this is every, I think, 15 minutes data, 3 hours data, continuously. And you can see first, the rainfall increases, okay? As the rainfall increases, water vapor goes up because evaporation increases. Then comes, once the water vapor is a critical value, in this case, 54 km squared, sharply it rises, okay, to a very high value, and then it comes down, okay. This is the first paper I've seen which has looked at the relationship between water vapor and rainfall at a very high resolution. Normally we don't see it because we don't have data, okay. So this is unique data from West Pacific, both satellite and I think ground-based data, and it shows water vapor has to go up for you to have deep convection, and once it goes on, there is deep convection, and after that it goes up even further, and then it comes down. Okay, so keep this in mind. This is very important to understand that water vapor has to go up before rainfall, and it decreases during rainfall, and then it comes down. Now that shows why if you plot column water vapor with rainfall or cloud top height in this case, it will be a highly nonlinear curve. So this is the most important result connecting water vapor and rainfall. The relationship is not linear, it's nonlinear. The question is, why is it nonlinear? Okay. Now, I want to show this nice animation. I want all of you to keep looking at it. It's available in real time from the Wisconsin website. It shows how water vapor evolves in time and what role it plays. And the key point is that only in the tropics, water vapor is plenty. If you are in US, you can see only these little, what they call rivers, atmospheric river. When they reach California, they cause rainfall. Otherwise, this region is dry. So these things spin off the tropics and reach some region here. But in the tropics, you cannot call it atmospheric river because they're everywhere. It's not unique. But if you go to mid latitude, you can see it's a very unique, sharp structure like a river. Okay. Now, this is another interesting result from Gilles showing how the profile of water vapor depends on rainfall. Okay. Note that the profile is got a fairly standardized shape, which is nice. Okay. It has a scale at about 2 kilometers. But there's a small dependence on rainfall. Not very large, there's some dependence which is important. Now, this is how people study rainfall. This is from one of Wang and Lee's paper, in which the connection between energy transported from surface, radiation, free tower flows, all these are connected, okay? But we will not look at this. This is more complex. Some of the others may look at it. So, since water vapor influences the rainfall in many ways, we want to come up with a simple model to explain how it does. And there's another paper on Nealon, which I like very much, which shows the relationship between rainfall and water vapor is dependent on the mean column temperature. Okay? Now, there are two ways of interpreting this. The standard way, many of us do it, is to say that the mean column temperature controls the stability of the atmosphere. Okay? That's not wrong, but that's not necessary. You'll see that. So the point is that as the mean column temperature goes up, okay, for the same amount of water vapor, you have less rainfall. Okay? So one way to interpret this, which is not wrong, but I don't agree with that, is to say that atmosphere becomes more stable, and so for the same water vapor, less rainfall occurs. Okay? But in my view, if you look at what I'm going to present later, what it really means is that as the temperature of atmosphere goes up, more moist energy is exported, and hence less mass can converge. To me, this is the correct interpretation. This is my view. No one agrees with me, but I want you to think about it. Okay, there's one more result. This is water vapor 3 hours before and the rainfall at the present time. You can see that water vapor 3 hours before is a predictor of what will happen 3 hours later. Okay. Now, according to climate models, the land sea contrast will increase because land will heat up faster than ocean. Land has low heat capacity. So you can, for example, there was a big argument last year about global mean temperature reaching 1.5. Okay, but the land temperature went to 2. Nobody talked about it. All the heat waves, all the problems we have is because land is heating faster. Although the land ocean is increasing, circulation is weakening. Okay, nobody is talking about why. Why should circulation weaken when land is hotter than the ocean? You'll see what my conclusion would be. Okay, the other thing which is unique to India, which all of you should know about, is Indian rainfall comes because we get water vapor from the Arabian Sea. Okay, no water vapor comes from Bay of Bengal. 0. Okay, you may not believe it, but recently all of you look at a paper published by Dipanjan Das, Lagrangian method, which is very nice. He shows not a single particle from here reaches India. Okay, so the unique thing about India is water vapor comes from Arabian Sea. The systems come from Bay of Bengal. The system's job is only lift water vapor. That's all. Remember, atmosphere is stratified. You cannot move anything up easily. Somebody has to move it up. That comes from here. These systems move it up and it rains here. Okay? So remember that this is unique to India, that water vapor dependence is Arabian Sea, systems come from Bay of Bengal. Now, let me show an analysis based on Nealon-held energy budget, which has already been discussed by Berdoni, but a little more detail. Now, I want you to remember that monsoon is a heat engine which converts sun's energy into vertical motion and rainfall. That's what it is. Okay? Now, to me, it has a lot of similarity to a similar model proposed by Emmanuel about cyclone. I liked it very much. It was published almost 30 years ago. He treated cyclone as a Carnot engine. Carnot engine's boiler is here, condenser is at 10 kilometers. Beautiful example. Of course, that's a very artificial example. He had a steady state cyclone, which doesn't exist in the real world. So he had a steady state cyclone. He showed how the cyclone's ability to get the condensation depends on this delta T. Okay. So this is what controls that counter cycle. Now, the work I'm going to talk about is based on Held. I'm sure already has been discussed by Bellon, and I consider it to be the most original work in Monsoon. It has not got the kind of attention it deserves, okay? So their argument is that you look upon this region of ITCZ, where because of the energy available, moisture is transferred up and it comes back in the cycle, okay? And so this is a model of Nilner, published in 87. And based on that, I developed a diagnostic model of the monsoon. And the first is a dry static energy. All of you know about it. And of course, moisture budget. And you add the two, you get the moist static energy budget. Now, what is special about this, which is not appreciated by most people, is in this equation, latent heating is there. Okay? So all the discussion in meteorology is latent heating drives the monsoon. It does not. Okay? It's totally wrong. But that is the popular understanding. Now, because it's unknown quantity, this will only happen when there's vertical motion. The clever thing that Nilner did, they added these two equations, it disappears here. In the moist static energy equation, latent heat does not appear. It is not a part of the equation, so you don't have to talk about it. Okay? All the fluxes are, this is sensible, radiative, evaporative. That is Q-div. So Q-div does not contain latent heating. Okay? So I like it because it can be thought of as an external driver of the ITCZ, okay? Not internal part. Okay? So this is the equation which was derived by Nilner Held. Now, all I did was, now remember that this equation has an approximation. It neglects horizontal advection. Okay? This is a part of the belief in WTG, weak thermal gradient. People thought if there's a weak thermal gradient, there will be weak moisture gradient, there will be weak moist static energy gradient. Okay? I also thought that those two terms are removed happily. Okay? And I solved this equation. Okay? But it is wrong. I want you to remember, they can get a good answer by doing something wrong. Okay? I don't know how many of you know. The most famous example all of you must know about is the Planck's equation. Planck's equation was derived by Planck with a wrong set of assumption. The person who corrected it finally was Einstein and S.N. Bose. I don't know how many of you know. S.N. Bose wrote a letter to Einstein correcting the derivation Einstein made. First mistake was Planck. Einstein improved it. There was a problem there, and S.N. Bose corrected it. Please read it. It was published exactly 100 years ago, 1924. Please read that paper. It's available on the internet. Okay, so this model is what I'm going to use. So once I neglect the horizontal advection, we take a ratio of these two equations, the vertical velocity, its magnitude will not be relevant. To me, it's a very important development, because all of us say more vertical motion, more rainfall, and so on. But the actual magnitude of vertical motion is irrelevant. You'll see that. When I take a ratio, omega appears here, omega appears here, right? So you write omega equal to omega max times some shape function, omega max disappears. To me, that is the most elegant part of Nilner Held hypothesis, although they don't highlight it. So they are able to get a result which does not depend on omega max. Okay? So, but this vertical integration you're doing is very sensitive to the profile of omega and profile of m. Okay? For example, one of my students we're going to talk about in this program later, Chetan Kumar Jalihal, he showed that between ocean and land, there's a big difference, because our ocean, omega maximizes at a much higher level than our land. Okay? Because there's more deep convection there than here. So that alters the integral dramatically. Okay? Huge difference is there. Now, I use a simple model because I wanted an analytical solution. I use something which is not correct. I wanted a simple analytical result. So I assumed a simple parabola, which is valid only if the maxima is at 500 millibar, which is not. Okay? And I assumed a simple lapse rate, which is okay, it's not bad. I assumed a simple structure for humidity, which is reasonable as you saw. And if you do all that, you'll get a quantity related to, I'll show you, this quantity which depends only on water vapor, okay? And this does not play a role. I want to remember this plays no role. Okay, so this delta, which I'll show you later, is a function of water vapor based on Renaissance data. So this is the equation finally I get, okay? Very simple equation which says that the rainfall and evaporation, moisture convergence, depends on amount of energy available at the top of the atmosphere over land divided by a constant which depends on vertical structure of m and omega and the total water vapor. Okay? One cannot think of a more simple explanation of the ITCZ. Okay? Now, how good is the model? Now, before I go further, I want to show you how the model, although it's approximate and has flaws, is very useful to understand the role played by incoming radiation. This incoming radiation has changed in the past. If you look at the monsoon over India over the past 10 million years, data is available from proxy data, S will keep changing because of the Earth around the sun. And this is albedo, which depends on clouds and which depends on aerosols. And then here you have OLR, outgoing long wave radiation, which depends on the water vapor, clouds, and carbon dioxide. So this simple model clearly shows you what role is played by various parameters in the denominator, sorry, in the numerator, which is the energy available. This is the energy absorbed, this is the energy emitted to space, this is what is available. If this quantity is negative, you cannot have ITCZ. Okay? That is a model prediction. As a matter, I like this model very much because it predicts when ITCZ cannot occur, and it can be verified. One of the important things about science is you make a prediction which is verifiable. Okay? You don't make predictions which are non-verifiable, it's useless. This can predict, no other model can do that. Okay? And then you come to the denominator, which has a simple structure because of the assumption I made. It shows this plays a role and this plays a role. This value is different over ocean compared to land, and this is similar in land and ocean. Now, to make this point even more fundamental, I want to call this as mass convergence. Amount of mass which converges in that is, it depends on energy available and the vertical structure. That multiplied by water vapor is the moisture convergence. Okay? So I'm making a statement which most people don't agree with, that the mass convergence is that does not depend on latent heating, does not depend on dynamics. Okay? I can tell you it is very unpopular. Nobody likes it. You will see in this program, a lot of people talk about dynamics, thermodynamics. They are so closely coupled, you cannot separate them. Okay? I can give you one example. One example give you very popular in many papers published, which says that the moisture convergence is, yes, all of you know that, okay? And they write it as rho this is how it is written. There are many papers published calling it thermodynamic and dynamic, okay? Very popular, but it is meaningless. So the two are connected. This is depending on thermodynamics, okay? This quantity is related to that quantity. So by separating it this way, Madhava has pointed it out. This is an artificial way of dividing convergence. It is not correct because the two are so closely related. Okay? So I want you to remember that the amount of rainfall that can occur over India on a seasonal mean depends only on net radiant top of the atmosphere and the vertical structure, nothing else. Okay? Yeah, so this is what rainfall over, this is a key point. Rainfall over sufficiently large area and period must be consistent with thermal conservation laws, okay? And they clearly say the border between dynamics are not yet established. What is the, which is dynamic, not slope connected, okay? Now, so the model that I proposed, I compared the seasonal cycle and monsoon in 4 different regions in the world. India, this is South America, this is North Africa and South Africa. The agreement between observation, read, and model is not perfect. Obviously, with all the approximations, you can't get an exact fit. But I would say this is the simplest model which explains the seasonal cycle of rainfall. I can't think of any other model which gives a simple explanation why rainfall occurs. It does not depend on land-sea contrast. It depends only on energy available and the moisture increase in the monsoon season. Okay? Now, to point out how good this model is, this model explains why there is no monsoon in North Africa, which is at the same latitude as India. Okay? As a matter of fact, this was pointed out 100 years back. Cherrapunji is right here, the highest rainfall in India, and here is Sahara. Why should, in the same latitude, that analogy is not good. Cherrapunji is orographic rain, so I will not talk about it. Look at central India, there's not much orography. That rainfall is much higher than here, all because central India gets 90 watts per meter squared. Africa gets 20 or negative. Okay? So the key reason why African ITCZ didn't move further north is because net radiation is negative in Sahara because of the high reflectivity of the Sahara Desert. Okay? And low water vapor. Those two are working together there. And to make it clearer, I'm showing you the rainfall contours along with net radiation. You can see clearly it is confined to a region where net radiation is large and positive. Okay? And then I want to show you that this is comparing RB data and GPCP rainfall. I want to show you that many GCMs don't get African rainfall correctly because their net radiation is too negative. Look at UK Metropolis, it's too negative. This is the correct observation. This is too positive. So go look up the data, you'll see MP rains too much over Africa. This rains too little because both of them don't agree with observation. Okay? So this shows clearly very important for your radiation code to be able to correctly predict the net radiation. Okay? And remember, net radiation also influenced by aerosols. Now, as a matter of fact, all of you know that Africa had a very difficult time about 40 years ago. They went through a long drought period from 1960 to 1980, and whole countries went bankrupt. And that is primarily because aerosols from Europe entered Africa. Okay? Once Europe implemented the Clean Air Act in 1970s, aerosol disappeared, African monsoon came back. So I don't know a better example of the role of radiation in monsoon. Okay, now I just want to quickly compare, more of it will be discussed by Chetan Jalia later, the difference between Bay of Bengal and India, the monsoon, okay? Bay of Bengal, it rains more than India. Water vapor is quite close, maybe a little higher in Bay of Bengal. The main reason is Bay of Bengal, being ocean, gets additional energy from the surface. Bay of Bengal stores heat from January to May from the sun. SST goes up, and with wind speed being there, it produces, so the Q div in Bay of Bengal is much higher than Q div over India. India cannot supply any energy from below. All the energy comes in, goes back. Okay? Net is zero at the surface. Ocean, because of the high mixed layer thickness, there is a lot of energy stored. That is what is giving extra energy, and that's what makes Bay of Bengal always higher than India. Well, it's a repetitive, I'm sorry. Yeah. Now, one more thing which this model shows, which I like very much, is what happens with global warming. Okay? With global warming, water vapor goes up, all of us are happy, more rainfall. Not true. For the same water vapor, you'll get less rainfall. Okay? So, in the future, you're going to have more floods and more droughts. So, this shows clearly, this is in a GCM present climate, future climate, because of the increase in water vapor due to global warming, the entire curve shifts to the right. Okay? But if the water vapor is same over India, you'll get less rain. And as a matter of fact, till about 5-6 years back, half the models said due to global warming, rainfall will decrease, half said rainfall will increase. There was no consensus. Now, most of them are saying it will increase. And so that depends on how high a water vapor goes up. Okay, that's a key issue. In your model, water vapor increases rapidly, then you'll be here and you may be having same rainfall or maybe a little higher. But if the water vapor doesn't go up too much, then you are in trouble. Okay. Now, the model I showed you just now has a flaw. The flaw is that you have to include this term. Okay. That term on regulatory Indian held, and so did I, and that's a big flaw for India. Other parts of the world, not so much. Over ocean, there's no problem. Ocean, this term dominates. But over India, this term is not negligible. Now, I can tell you this is counterintuitive. See, if you talk to anyone about WTG, they will tell you in the tropics, gradients are weak. dm dx is small, dm dy is small. So this should be smaller than this. But this integral is very interesting because omega and dm dp vary in a slightly different way. The sum, when you integrate, has a positive part and a negative part. When you average, you'll get 0, almost. So that is the thing which is happening in India, because omega is at a lower level, this integral goes to 0, and so this term becomes important. Okay? If this term becomes important, you cannot get a simple model. Model gets complicated. But my student looked at it, this is the term which he found to be important. Okay? So WTG cannot be used to justify declaration of this. But so we defined a new term to extend the null hypothesis. We called it total GMS instead of GMS, which is the word used by Nil for what I've used. Total GMS includes all the horizontal advection as well as vertical advection. This term is more complicated. You cannot get a simple analytical result. But what Chetan did, he was able to show that, I'm not showing it here, he was able to show that even though this is quite complicated, if you don't look at seasonal cycle, if you look at a 100-year average, which is relevant to paleoclimate, it depends only on water vapor. Okay. So those of you who are not going to be there can look it up later on in the recording. So what is interesting is this TGMS, because of this term, depends on dynamics. Okay. When I developed, dynamics didn't play any role. Okay, people didn't like it. But now dynamics plays a role through this term. But the role of dynamics becomes lesser and lesser as we average a longer time scale. So you go to 50-year, 100-year, that thing gets suppressed. Okay. So over a 100-year time scale, this depends only on water vapor. Okay. Using that, we were able to show why the monsoon in the present climate is much higher than the monsoon during the last ice age 20,000 years ago. Okay? The difference in these two is mainly because of water vapor. The last ice age, the temperature was so low that water vapor was much lower, okay, compared to present climate. So this is very good to use for long-term climate studies. Okay? Now, so this now depends on many things, not just water vapor. Okay. Now, this is what Chetan showed. He showed that the rainfall increased rapidly after the last ice age. This is based on simulation by an NCAR model, but observation also shows the same structure. This is the incoming radiation. Okay, you can see it's a very dull variation. Radiation was low at this time, it became high and again became low. But rainfall varied much more. Okay? You can only explain this through the fact that TGMS depends strongly on water vapor. Okay? Otherwise, you cannot explain it. As a matter of fact, before this paper was published, most of the paleoclimate people argued that rainfall depends only on incoming radiation. Essentially, they ignored this term. They said this is the dominant term. All these are constant, this dominant term, which is true if you look at very long time scale. If we average over 100,000 years, yes, this variation will not be there with water vapor, but over this period, this large increase can only be explained because TGMS depends on water vapor, not on radiation. Okay? Yeah, this is the comparison between the black, which is the GCM, and CAR. Red is this model. Now, I want you to appreciate that we are able to get a simple analytical solution for ITCZ over such a long period. Okay? This shows clearly the dependence on incoming radiation and on water vapor. This number is different from what I got because you and we also play a role. Okay? Now, this is the fit he got of the total GMS with 1 hour water vapor. It's almost linear, not quite. There are a few spots which are departing from that. So I'll conclude with this statement that paleoclimate people said rainfall in the monsoon depends only on incoming radiation. They are right when they look at scales of 20,000 years and more, absolutely right, no problem. You can draw a linear fit. But if you look at this scale, which is what Chetan looked at, it depends on water vapor. But if you look at smaller scale, then it depends on incoming radiated water vapor and vertical moist stability, how the moist static energy varies with height. Okay? And if you look at interannual, it's even more complicated. Okay? Depends on dynamics. Okay? So the key point is, dynamics is very important when you go year to year. It becomes less important on decadal and longer time scale, and on very long time scale, only that's important. Okay? So you'll see more discussion on this from Chetan. Okay? Let me conclude. The monthly seasonal mean rainfall is related to energy available and vertical structure of the moist static energy and vertical velocity. Magnitude of the maximum velocity does not play an important role. ITCZ cannot exist in regions when net radiation is negative. The mass can converge determined by enigma, not dynamics. Okay? This is my fundamentalist view. I have not converted enough people to it, but I hope more of you will be converted to that. Thank you.
Thank you, Jace. I think we have enough time to take questions. Yeah. Can somebody pass in the second row?
Yeah, you have to translate. I can't hear it from there.
Sure,
you tell
sure.
me. Yeah.
I will repeat it.
Thank you for the talk. So I just wanted to ask that you just showed a total column water vapor and precipitation plot from
Yeah.
I think Neil and Held, but in that paper they have done a lot of binning and they kind of divided the total column water vapor into different 5 mm bins.
Your translate. I can't hear it. Okay.
Yes.
Okay.
So he's
Yeah.
saying that the paper by Nealon,
Yeah.
which shows the precipitation versus precipitable water
Yeah.
scatter, they have done a lot of binning while showing the non-linear relationship.
Yeah. You have to do that. There's no choice.
Yeah,
See,
but if you look
at our
into
subject, if you don't average, you'll get noise. You have to average, there's no choice. Only question is average over what time scale and what spatial scale. You have to see the real progress occurred in our field only when people chose the correct spatial scale and the correct temporal scale to average. Okay? If you don't average, you'll get all over the place. Because there are thunderstorms, there are cyclones will come in your data. So you have to average. There's no choice. Okay?
Yeah. Okay.
You have to, if you want a simple answer, you have to do some spatial and some temporal averaging. Otherwise, it will be very noisy. Okay?
Yeah.
That's the penalty you have to pay. You cannot explain rainfall at an instant. That is a highly random phenomenon. Okay? I'm sure more of the speakers will highlight how complex rainfall is on a smaller time scale. I'll give an example. Just about a month back, It was raining heavily here, but not in our institute. Just 10 kilometers away, even less, as the crow flies. Spatially highly variable, okay? So if you want to discuss rainfall, you have to average over sufficiently large scale. Otherwise, you will get very complicated phenomena. Okay, you have to accept that fact.
Do you have a follow-up question or?
Yeah, so basically what I was asking that if we don't do the binning, the scatter actually comes really like it's all over the place. Like there would be a lot of points when total column water vapor is very high, let's say 60 mm, but there's like barely any precipitation. So when you just mentioned that just before the rainfall, just before the onset of the rainfall, the total column water vapor must increase. But there are a lot of points when even though the total column water vapor is high, there was not much precipitation, which comes back to the question that even though high total column water vapor is one of the necessary condition for the rainfall, but it's not sufficient for the rainfall to occur. So there must be some other physical process that triggers the convection. So I just want to know your idea about that.
Okay, let me tell you, I'll give you an analogy with the El Nino phenomenon. All of you know El Nino phenomena, right? Now, for a long time, there was a big fight between the oceanographers and atmospheric people, which was more important. Finally, philanderers settled with saying, it's a coupled system. Okay? Same thing is true about water vapor and rainfall. Each is connected to the other. It is not independent. Okay? So you must appreciate that, first of all, you bring water vapor into a column for it to be sufficiently unstable. Okay? So in India, it's a pre-monsoon showers which bring in that water vapor, okay, thunderstorms and so on. That's a prerequisite. But after that, it is the water vapor which determines how much rain will occur. Okay. So you must remember that one cannot, in our subject, cleanly separate the cause and effect. They are connected together. One affects the other and the other affects this. So you cannot have a simple, neat result, which I would like to have, but not possible. Okay? But I can tell you, those of you now have access to high quality reanalysis data, you can march and check how the rainfall, water vapor changes every time step and try to figure it out. Because today you have good data available, okay? You don't have to look at monthly mean. You look at your result and see in time how the water vapor goes or rainfall goes up and figure out whether you can see the connection. Okay?
Nice presentation, sir. Yeah, I am Sripati. Sir, in the Tibetan Plateau region, the surface temperatures are cooling. That paper, I forget that paper. So normally the diabatic heat source of the monsoon system, like that is in the Tibetan Plateau plays a key role for the Indian summer monsoon time.
He's talking about the elevated heat pump hypothesis. Elevated heat pump hypothesis.
Yeah.
He's saying, but Tibetan plateau surface temperature.
Yeah, see, there is an elevated heat pump hypothesis of Love you're talking about, right?
Yes, sir.
Bill Love.
Yeah.
I don't believe it. I can tell you, it came in the context of black carbon, you know that.
Yeah, yes, sir.
Black carbon. We don't have sufficient high quality data to demonstrate how much heating is caused by black carbon. Okay?
Okay.
And I can tell you the quality of the models we have today, when you put aerosol in a model, it's very tough. Aerosol plays two roles. One, it heats radiatively the column. Secondly, it affects the cloud.
Yes, sir.
The indirect effect, okay? In most models, indirect effect is more important than direct effect.
Okay.
Okay. Now, I would have been very happy if Love had taken a model and suppressed the indirect effect and shown this, then I'll be happy.
Okay.
Then there's no problem. You have to suppress the indirect effect because that is more important than direct effect. Okay?
Okay, sir. Next.
Yeah, I'll tell you why. A lot of people have done black carbon work because there's a political component to it. All of you know about it, I suppose. Yes, because in year 2005 or so, the president of US, Bush, pulled out of the Kyoto Protocol saying that black carbon is causing more global warming than CO2, which is junk, okay, which is nonsense. But he used an excuse to get out. And after that, a lot of work was done in America to show black carbon is the culprit. It is not, okay. Black carbon among the atmosphere is 1/10 of sulfate, okay.
Yes, sir.
Sulfate emission is very high. It was high in Europe, America, and China. Now it's gone down. Okay, so sulfate has a huge impact on the Indian monsoon by reflecting sunlight. That's very clean. Okay, but the indirect effect is very tough, because all of you know, you'll find out more in the next lectures. Very few GCMs correctly take care of the role of aerosol and clouds. Okay, you don't have sufficient observation. You don't have sufficient understanding about how aerosol affect the clouds. And so the indirect effect is not the same in different models. So we don't know what's happening.
Okay, sir.
We run models, but we don't know what's happening, because indirect effect is sensitive to cumulus scheme and radiation scheme. Okay, so the so-called elevated heat effect may be there in the pre-monsoon season, yes, but once the rainfall occurs, PC goes out.
Yes, sir.
But I'm not saying a clean result. I wish Love had removed the indirect effect, then I would have agreed it is correct.
Okay, sir. Another question. Nowadays, the June rainfall.
By the way, if you want, you can read 2 or 3 papers I published with Arindam, in which we don't put aerosol, you put the heating of the aerosol.
Okay, sir.
That is a clean result. And we have shown both the remote impact and the local impact. Okay, 2 papers are published. You want to know, I'll send it to you.
Okay, I will come, sir. Another question. Nowadays, the June rainfall is decreasing. Like extreme events, like when you compare to the onset days delaying.
Okay.
So, in your contrast, the like water vapor present in the atmosphere is more than the rainfall is also, like onset is both are in the water vapor is more than that maximum rainfall onset is also there. Then it will decreases.
What will decrease?
Like that slide, I think.
Are you saying that there is a delay in monsoon onset?
Yeah.
Can built up of precipitable water explain this delay?
Yes, sir. Yeah, yes, sir.
No, it's not that simple. I tell you, in the June month, I can tell you, June month, your increase in water vapor depends upon pre-monsoon showers. Okay, I don't think anybody has simulated correctly. It depends on how much of thunderstorms occur in that area to build up the water vapor. Okay.
Okay.
So I've not seen a very credible model which correctly reproduces water vapor in June on a day-to-day basis. Not easy. Okay.
Okay, sir.
So there's a whole discussion here. Maybe you can talk to people who will talk about it. Because the
synoptic
onset phase is the most difficult part of the monsoon, this one. And I have not seen people demonstrate that their GCM correctly reproduces the observed water vapor increase. So remember, today we have a high quality water vapor data from satellites. Okay, very good data is there. I showed you that animation.
Yes, sir.
So somebody should find out which GCM, I'm talking about forecast, not climate, correctly reproduces the water vapor evolution over India. I have not seen that paper yet. It shows that their model correctly gets the increase in water vapor.
Okay, sir. Thank you, sir.
Yeah, this student in the 3rd row.
Hello, sir. My question is that you mentioned that in monsoon rainfall, water vapor purely comes from Arabian Sea. But I want to know what about monsoon depressions, which is also a rain-bearing system during...
No, monsoon depression only creates condition to lift water vapor. Monsoon depression does not bring water vapor. That's why I want you to read dependent days Lagrangian formulation. See, all of us use Eulerian, okay, very convenient. But the best way to understand is to follow the particle, okay? So read the paper with dependence, very nice paper, okay, in which it shows almost no water vapor from Bay of Bengal reaches India. Almost zero. Only water vapor Bay of Bengal goes to Assam, goes to Burma, doesn't come to India. Okay, it's a very nice paper, and this is to be under everyone that all the water vapor comes from southern Indian Ocean, Arabian Sea into India. That is how the Somali jet comes. Okay, so this is very counterintuitive. I can tell you, Professor T.N. Krishnamurthy, one of the great monsoon researchers, he told us 20 years ago, I didn't believe him. He said, water vapor comes from Arabian Sea and the systems come from Bay of Bengal. These systems don't bring moisture. The moisture is already there. I'll give you the best example. Take Rajasthan. If you have been in Rajasthan, in the month of June, there's water vapor because it's come from Arabian Sea. There's no rain. Until the systems come from the Bay of Bengal to Rajasthan, there's no rain. But you can look up, water vapor is always there. Okay, somebody can plot water vapor from reanalysis and check how much water vapor is there in the Rajasthan. It's not very high, but it's comparable to some places in Maharashtra and so on, but it won't rain because it's not lifting up. So the role of those lows, depressions is to push the air up. Okay.
Thank you, sir.
Oh, if we want to let the students go first, it's totally fine. Okay, great. No, I just wanted to make a comment on your point 3 that goes back to sometimes the importance that horizontal advection of temperature and moisture can have.
Yeah.
So I totally agree that in the deep tropics, you can only have this export of energy and therefore ascending motions and ITCZ when you have net positive, net energy input. We looked with a student of mine a few years back at the Mayu-Bayu front, which is further more in the subtropics.
Yes.
And there, if you look at the energy budget, you find that there is basically no energy input. And yet you have convection. In the Mayu-Bayu, what you would call the East Asian monsoon, the rainfall band, the Chinese monsoon.
Chinese.
Yeah. Input, but there is still.
Let me explain to you. My view, Chinese monsoon
is not a monsoon. I agree.
Mid-latitude monsoon.
Well,
it is not tropical monsoon.
It's mixed, right?
What is the latitude?
Yes, exactly, because it depends where you look. I totally agree that as you move further downstream over the Pacific, absolutely, that is much more mixed. There's mid-latitude storms, but if you
so
go.
What I would argue is that.
No, what I was going to say is that if you look at this moist static energy budget framework, what helps you is actually that you get advection of warm air and moisture. And so the balance still holds. It's just that the vertical motion basically balances the fact that you have warmer and moister air. So import of moist static energy is from the horizontal
what area
direction.
did you average the net radiation?
Yeah, so we looked a little bit at spatially, but in general, if you think about the Chinese and the Bayou, which is the extension on Japan, the Mayu season, yes, but again, this is
But
to
it's
say...
above 30 north, right?
Exactly. As you move further...
I won't agree. I will not
absolutely.
apply NH above 30 north.
Actually, it still works. It's just that the energetics is maintained. It is maintained differently.
But if you look at
again, it goes back to the point that you were saying that as you move a little bit away from the deeper tropics, this idea that it's all weak temperature gradient or weak moisture gradients does not apply. And in fact, word by needing that show that the advection, the import of lower moist static energy air is what sets the polar boundary of many monsoon regions.
But I would like to say, if you now extend nil hypothesis, include U, dm, dv, dm, dy. One thing, he did some work, he didn't publish it. GMS can be negative.
Mm-hmm.
Know that.
Absolutely. Yeah.
So maybe GMS is negative there.
Yeah.
See, normally over land, GMS is not negative.
Yeah.
But he found in his doctoral work that in the southern ITCZ, GMS is negative. Okay. When there are two ITCZ, one is negative, one is positive. Okay. So if GMS is negative, it's okay.
Yep.
Yeah. But over land, we are not seeing GMS negative so far, but we have to check it. It's a very good point. If you tell me what paper it is, I'll look at it.
Yeah, sure.
Definitely.
Yeah, but I wanted, again,
It's
to make the
counterintuitive,
comment that, again, this moist static energy budget framework has been, it has really revealed a lot of the important aspects of monsoon, including how, again, the fact that there are situations where the horizontal advection of moist static energy is important.
Yeah.
But thank you very much for your talk.
It's a good point, yeah.
There's one question, I think, there, and that would be the last question, unfortunately.
So regarding the moisture, the water vapor source coming from Arabian Sea, was that about only the Indian monsoon or in general about the South Asian monsoon?
I would say, although you go back, look at it, people don't know. Indian monsoon is unique. We get water vapor from Arabian Sea, okay? Ask about African monsoon. We get it from Atlantic Ocean. Okay? But I've not seen a detailed work on that. I'm yet to see a good work showing, because we know the Atlantic SST affects Sahel rainfall. Okay? That means water vapor that plays a role. Okay? I'll tell you the most interesting piece of work, which is not yet published, which Chetan did, who's going to talk about later. You reverse the rotation of the Earth, okay, called retro simulation. All of you know that. It's called retro, very popular. Just change the value of F, okay? Sahara becomes completely monsoon domain. Whole of Sahara in about 1 week. So that to me is the most powerful demonstration of the role of water vapor in monsoon. We just change the rotation. After 10-15 days, the moisture from Arabian Sea goes into Sahara. Sahara overnight becomes totally wet.
Yeah, my question was yes, sir.
So that's the only time I can think in a transient simulation. See, I'm talking about a steady state, okay? That is very simple. This is a transient simulation. You can march in time and watch how water vapor goes up and alters the QNet, and hence the ITCZ suddenly. You can look at it in a what you call a transient process, okay, which I like very much. He's not yet published it, unfortunately, and he's not talking about it this time. You should encourage him, because to me that is. By the way, all of you can do that simulation. You don't need fancy computer. Okay, you keep SSD constant, change the rotation, run for about 2 months. You will see everything will change. Indian monsoon won't change. Why? Indian monsoon will get whatever from Bay of Bengal. Okay? Indian monsoon is safe. Sahara gains, Indian monsoon doesn't lose. Because we have warm ocean both sides. Okay, we are lucky, we have 2 oceans, both are warm. One gives you system, one gives you water vapor. Okay? So when you change the rotation, it doesn't change.
Yeah,
so to me, that is the best illustration of the role of water vapor, because what I'm showing here is not totally convincing, because it is a steady state model. Okay? I'm not telling you how water vapor came. You do a transient simulation, you get a much better insight.
Okay. Yeah.
So all of you can do it using reanalysis data. Today, I consider ERA5 to be an excellent source of almost, you have about 80 years data. So all of you can look at it, okay, and see how much you can understand about monsoon.
Okay. Can I continue? Like the
Yes,
actual
quick question.
Yeah.
One and a quick one.
The source of moisture from Arabian Sea seems quite convincing when the monsoon has established and the circulation, we have the low level jet coming from the west. But in the initial phase of the monsoon onset, the Arabian Sea is filled with northwesterlies, and much of the...
That's a very good point. You made a very good point. Good, you reminded me. The beginning of the monsoon is at the Bay of Bengal. Okay, Bay of Bengal gets the first monsoon, not India. That generates the Somali jet. We have shown that Somali jet strengthens 3 days after the Bay of Bengal rain. Okay, so remember, look at the animation. The rainfall comes from Australia to Indonesia, East Asia, Bay of Bengal, then India.
Yes.
So that heat source over East Asia, Bay of Bengal was Somali jet. Somali jet is triggered by that.
Yeah.
Okay.
Yeah, maybe the initial source of moisture is local.
If you look at the jet strengthening, it starts with Bay of Bengal. Okay.
Yes. Yeah. Okay. Yeah. Thank you.
Thank you. Let us thank Professor Srinivasan.